In part 2, we learned all about texturing, and in part 3, we're going to be talking about transparency and alpha clipping in our shaders. In forward rendering, which is what URP uses by default, Unity renders your meshes in 2 steps. Firstly, all the opaque objects are drawn, but we'll mostly worry about those in part 4, which is about depth testing. Then secondly, we render all the transparent objects. The most common method is called alpha blended transparency, where the fourth component of the color output, known as alpha, is used as a weight factor where, for example, an alpha of 75% means that the screen pixel color is 75% the mesh's color and 25% the color of whatever was behind the mesh. This means that we need to process transparent objects in a back-to-front order to ensure that we get the correct output, but Unity will handle the sorting step for us. Let's branch a new shader from the basic texturing shader that we wrote in part 2 by duplicating it, then I'll name the copy Alpha Blended Transparency. I'll also use that name on the first line of the shader file. It's very straightforward to add Alpha Blended Transparency to any shader. First, in the tags block, I will make both the render type and the queue use the value transparent. When you do that, Unity will start to draw any object with the shader in the transparent queue, so it will be sorted back to front and drawn after all the opaques. Doing this doesn't make the object look transparent though. To do that, inside the pass block at the top, we use the blend command, which needs 2 keywords to come after it. To explain these, it's best to think of the mesh we are currently drawing as the source and the screen we are drawing to as the destination. We will multiply the source color by some factor and the destination color by some other factor, then add the 2 resulting values. That's the new screen color for this pixel. The first keyword after blend specifies the factor that we use to multiply the source color, and for alpha blended transparency, we use the source alpha, abbreviated as SRC alpha. The second keyword is the destination factor, which we will use 1 minus source alpha. There is a handful of possible values for these factors, which we will explore later. The alternative for an opaque shader is to say blend off, but you don't need to explicitly write that. It's the default value when no blend option is specified. So to recap, we take the color of the mesh we are drawing and multiply by its alpha. Then we take the color of the screen and multiply by 1 minus the mesh's alpha. Then we add those 2 values and overwrite the screen color with that result. In the scene view, if we assign some materials using the alpha blended transparency shader to some meshes, we can change their alpha values and see those objects fade in and out of visibility. When the object has full alpha, it looks as though it's opaque, and when it has 0 alpha, it's completely invisible. It's nice that we can change the transparency level using alpha, but alpha blended isn't the only type of blend mode. With additive blending, we multiply the source color with the source alpha and add that value to the destination color. Or with multiply blending, we just multiply the source and destination colors and that's it. We could implement these as separate shaders or modes, but I'm just going to expose the blend modes for the source and destination so that you can set them at will. Let's start by adding a couple of new properties. The first will be called SRC blend, short for source blend mode, and it will use the integer type. There's a legacy type called int, which is actually a float in disguise, but I want to be thorough, so I'm using integer. Then, what do we put for the default value? What number represents source alpha? Well, the blend modes used by Unity can be found in an enum called blend mode, which I'll list on screen here. This page tells you what each one does. For example, 0 will multiply each component of your color by 0. DST color will multiply the red channel of your color by the destination red, then the green channel by destination green, and so on. This enum maps each mode to an integer with 0 indexing. So 0 mode is 0, 1 mode is 1, DST color mode is 2, and so on. For our source blend property, I want to use the source alpha blend mode, which is entry number 5 in the enum. Likewise, I will add a second property called DST blend, and since I want to set its default value to 1 minus source alpha, that's the 10th entry, so I'll use the value 10. It won't be good enough to expect someone using our shader in their material to know what all these magic numbers mean and type them in whenever they want to change blend modes, so we can force this property to appear as an enum dropdown. To do that, we add something called an attribute in front of the property declaration using a set of square braces. This will be an enum attribute, and then inside a set of parentheses, we put the name of the enum, which is unityengine.rendering.blend-mode. Now, if I save my shader and look at it in the material inspector, I can see the correct default values being used for both the blend mode parameters, and I can change them with this nice dropdown. We just need to link these properties to the modes used with the blend shader lab command. That's super easy. We put the source blend and destination blend property names inside sets of square braces like this, in place of the source alpha and 1 minus source alpha keywords that we used to have here. Now, if I wanted additive blending, I can set the source blend factor to source alpha, and the destination blend factor to 1. Or for multiply blending, I can set the source factor to DST color, and the destination factor to 0. Awesome! This is just one case where we can use properties entirely within ShaderLab without needing them in HLSL, as I mentioned was possible in part 1 of this series. With these settings, we can create semi-transparent objects, but next I want to focus on one question. What if I want to cut away shapes in an object easily based on its alpha? We do that with alpha clipping, where we can set some threshold value and then check if the output alpha of the fragment shader is above that threshold. If it is, then we can draw the object, and if not, then we can discard that pixel entirely. Clipping can be implemented into shaders in either the opaque or transparent rendering queues. I am going to branch off the basic texturing shader once again, and this time I'll call the duplicate alpha cutout, remembering to rename the shader on the first line of the file too. Let's add one new property, which I'll call alpha threshold. We could use a float for its type, but we know ahead of time that this value should always be between 0 and 1, since alpha can't really go beyond those bounds. So instead, I'll use the range type, which lets us specify lower and upper bounds for this property in the inspector. It's still a float under the hood. This is just useful for clamping values automatically, and Unity will display this property as a slider in the inspector. We can use a default value of 0.5. Next, let's modify one of our shader tags and change the queue to alpha test. This queue runs between the opaque and transparent queues, which means that any alpha test shader will be drawn after an opaque shader. However, for the purposes of sorting objects, it's still considered opaque, and we're still not doing any blending. We also need to declare the alpha threshold variable in HLSL inside the C buffer using the float type. Next, in the fragment shader, I will quickly refactor this code so that the first line calculates the base texture multiplied by the base color, and the return statement just returns that variable. In between these two lines, we need to take that color and discard the pixel if its alpha is below the alpha threshold property. There are two ways to do this. First, we can use the discard keyword. In an if statement, we can check if the output color, alpha component, is less than alpha threshold, and if so, we just write discard and a semicolon. Pretty straightforward, I think. The second way to do this is with the clip function. We pass a value into this clip function, and if it's below 0, then the pixel is discarded. With that in mind, I will pass the output color alpha minus the alpha threshold into the clip function. If output colors alpha is below the threshold, then this evaluates to a negative number, and the pixel gets discarded. There isn't any real difference between using either method, and I'd hazard a guess that the shader compiler probably compiles both to the same thing in many cases. It's mostly preference. I like the discard version better, as I feel it's slightly clearer what it's doing to me, but you can use either. That's all we need to do in the shader, so let's save it and check out our effect in the scene view. I'm using this grass texture on a quad mesh to test it out. The areas of the grass have alpha of 1 and the air outside it uses an alpha of 0. If we set the clip threshold to anything above 0, then the grass is going to look as expected. To be clear, this grass is still an opaque object. It still gets drawn just after the opaque objects and it draws to the depth buffer, although that's a topic that we will be exploring next time. Let's quickly recap everything we learned in this tutorial. Transparent objects need to be drawn in a separate queue after all opaques have been drawn to ensure correct blending. Alpha blended transparency mixes together the mesh being drawn and the existing screen contents using the alpha as a blend proportion. Additive and multiply blending can be achieved by using different blend factors, which we can expose to the inspector. Alpha clipping can be implemented into any opaque or transparent shader, and it discards some pixels entirely based on a threshold alpha value. We also saw new property types like integer and range, and used our first attribute to assign an enum to some of our properties. If you want some homework before the next part comes out, try adding alpha clipping to the alpha blended transparency shader. In the next part, we will be talking about the depth buffer and how to support reading depth information inside our shaders, and how to make sure our shader writes depth information properly, including our first look at a shader with multiple passes. Until next time, have fun making shaders.